We had that issue when Onur was lecturing also, right? I don't know about this one. Is it better? So this one we need to report. Maybe you can, I don't know, write the number or whatever, such that when we call them. Okay, it's already the time. Good afternoon. Welcome to lecture 15 in computer architecture. Today, I'm very excited about the topic, emerging memory technologies. We have discussed a lot about the scalability issues of DRAM. We will also discuss tomorrow and also next week regarding the scalability issues of flash memory. And we develop actually many different techniques and in order to improve scalability. But it's also good to look into other technologies that they can potentially replace DRAM, and they can essentially provide better performance, energy efficiency, and many other good metrics. So emerging memory technologies is a very exciting topic for me. I got to know about them when I was a bachelor student in 2008. I remember on 2010 or so, actually, I had a course in electronics, and in that we were learning about flash memory and also other technologies like PCM. And then I started actually talking with the professor, and he actually gave me some papers that it turns out that those papers were from Professor Mutlu. So that was my starting point with Onur, with Safari. That I learned about this emerging memory technology like PCM, flash memory, and and basically it happened to my journey also, my career. Okay, without more introduction, any questions? I think Konstantina actually announced the exam date, which I already also announced before in the class. But for the location, we reserve, we have this room. We also reserve ML-F38 beside this room. So we have 2 rooms, which we're gonna have for the exam. And to arrange it better. But maybe it's too early to talk about the exam. Okay, good. Okay. So yeah, we discussed about limits of charge memory. We didn't discuss much about flash memory. We're gonna see tomorrow and also the next week about flash memory and solid state drives. But DRAM, I think you know very well at this moment that essentially we store charge in the capacitor. So you store charge in the capacitor, and based on and using this transistor, access transistor, you read and try to sense the charge in order to understand, we store 1 or 0. Flash memory is also somewhat similar. So we store charge in the floating gate, and through some basically sensing circuitry, you can sense that charge to see what you have been stored. So the problem with charge memory is that essentially as we scale them and as we make these cells smaller and smaller, you cannot reliably store charge. And that's very fundamental to basically to overcome. It's not easy. And you have seen that. We and other groups actually work a lot in order to improve the scalability of DRAM cells, as well as also flash memory. But in the end, as you scale them smaller and smaller, this problem actually we're gonna hit you. So it's very hard to escape from that. Flash memory, actually, it was very interesting because around the year of 2015 or 16, in order to provide higher density, vendors actually tried to, basically they were scaling down flash cells a lot. And as a result of that, actually, flash memory, it wasn't really reliable back then in 2015, 16 or so. And our group also, we published a lot of papers during that time that we discussed about different techniques to overcome these limitations. And we're gonna also see later about them. But around that time also, vendors, they realized that they actually come up with another technology, and they realize that they can stack floating gate in a 3D architecture. And basically that gives them another breathing room, essentially, you know, that they can provide higher capacity by adding layers and not necessarily making flash cells smaller and smaller. But of course, now the question is that whether it's going to work forever. So it's not clear, because in the end, nowadays, they are adding layers, and also they are making flash cells smaller. So I think at some point, actually, the scalability is going to also hit here, and the problems will, again, come up. So it's very hard to avoid that scalability issue in charge memory, essentially. That's my point in the end, that's the takeaway message I have here. So we discussed about different techniques. The first solution that we actually work on it a lot is that come up with new memory architectures. So we want to overcome memory shortcomings with memory-centric system design, novel memory architectures, interfaces, functions, better waste management. For example, we discussed about the fact that we designed everything for the worst case scenarios, like the latency. For example, we discussed about different techniques to optimize for the common case, not for the common case, for the current case, or for a specific temperature, for the specific DRAM module that we are testing, and also similar ideas. So we look into different techniques, like to enable reliability at low cost, reduce energy, reduce latency, improve bandwidth. We didn't discuss a lot about all these techniques. For example, we didn't discuss much about how we can improve capacity. Like there are a lot of compression techniques that people come up in order to reduce the waste in terms of capacity. And also how to improve bandwidth efficiency. People come up with how we can utilize bandwidth better. Again, you can think of using compression. You can compress when you want to move out data, so that compression can help you to improve bandwidth utilization. We also discussed a lot about enabling computation close to data in the memory-centric computing. So many of these techniques actually we discussed, and we are still also working on them, because it's important to push that line as much as possible. And it's actually also not exhaustive list about some papers that we have published in this line. But it's also important to have another angle in the solution, which is emerging memory technologies. So there are some emerging resistive memory technologies that they seem more scalable than DRAM, and also they are non-volatile. So essentially they store, basically you don't need to store charge in these memory technologies. You can present the value essentially by some resistive value. And it turns out that with resistive, actually you can scale it much better. And basically you decide what you have been stored, like 0, 1, or something between, by checking the resistive value. As long as you have quite different resistive value among different levels of this memory, you can reliably basically assess the value that you have stored. So one example is phase change memory. It's actually not a new technology. It has been developed in 1960s, I guess, around that time, that they use, different materials like chalcogenide glass, which has 2 different phases, amorphous, crystalline, and amorphous, I guess. So it's essentially data is stored by changing phase of material, and data read by detecting materials resistance. So this technology has been used actually in CD, when they want to write in compact disk, and when they want to read it. And why is that? Because it turns out that these different phases of this material has different basically light reflexiveness. And so essentially you shine the light on the CD, and depending on how much light you get, you can assess you have stored 0 and 1. But of course, this is actually a very slow way to read. And that's why actually it hasn't been implemented much in the hardware, in the memory technologies that we need to access fast. But later on, actually, some companies like IBM, Intel, they have worked on it a lot. and also people in academia. And they come up with some circuitry that you can actually sense the resistive, because these two phases of this material can also have different resistive. So if you have a sensing circuitry, which using that you can sense the resistive that this material has at that moment, you can essentially detect what you have stored. So the thing is that this technology has better scalability. So it's expected to scale to 9 nanometer. This is the actual report in 2022. Also, we have a prototype of this PCM at 20 nanometer around in IBM, in this paper in IBM Journal of Research and Development in 2008. Whereas actually DRAM, it took, I think, around 7 to 8 years more later than this year, such that they can get to somewhat similar to 20 nanometer. So that gives you some idea of why this technology has better scalability. Like in 2008, they get to 20 nanometer. However, in DRAM, around 2015 or so, they get to 20 nanometer. But of course, this is also a prototype. It's not a complete memory that people can use. But intuitively, this architecture has better scalability. Also, this architecture and this memory cell expected to be denser than DRAM. And this density actually comes from two factors. One of them is you can scale it better. So you scale it more and more. And another important thing is that you can store multiple bits per cell. So when we have this resistive value, so one way would be, okay, encode it to low and high, low resistance and high resistance, and it's going to be only 1 bit per cell, right? But you can also chunk the window of different resistive values, for example, in 4 partitions. And then you can encode 2 bits, for example. Or you can, for example, chunk it to 8 stages, and then you can encode 3 bits. This is also kind of, people have worked on it on DRAM as well, to try to understand the charge in that capacitor and then try to encode it to 2 bits. But that complicates the sensing circuitry, like the sense amplifier, actually very much. So still, there is no really easy way in DRAM to provide that possibility. However, in PCM is actually quite possible, and people have shown that. So yeah, but the problem is that, these technologies are very good in many cases, but the problem is that they also have many shortcomings. And in some cases, actually, their shortcomings is even much more from the benefits that they are providing. So enabling these technologies in our system is very important. That's why people need to do research a lot and try to improve the architectures using these technologies. It does, of course, people from the device level, they are also contributing a lot, to improve these technologies as much as possible. But from the system and architecture level also, we need to develop a lot of techniques, to enable these memories basically more in our computer systems, essentially. Any question? Okay, yes. I'll show you later. Yeah, I'm not going to provide the exact sensing circuitry, but I will give you some idea about how this can work. Yeah. Okay, so essentially the question is that can these memory technologies, like emerging memory technologies, be enabled to replace completely, like using PCM completely completely replace DRAM, or augment it, like having PCM and DRAM together, or in some cases actually surpass DRAM. For example, these memory technologies, they have some characteristics which we don't have that at all actually in DRAM. Like, for example, this PCM and other emerging memory technologies, they are non-volatile. So potentially you can think of using them for persistent memory. Nowadays, when we want to have persistent data, we need to always go through the disk or solid-state drive, let's say. However, if you have a PCM memory using as your DIMM, that PCM can be used as your essentially persistent memory. And that can actually accelerate a lot. Even though this architecture, like PCM, is slower than DRAM, which we're going to see also numbers, but it's much faster compared to flash memory or also disk. So for those applications that you need to keep things persistent, it's much better. For example, this can provide much better performance. So that's we need to really, when we want to work with emerging memory technologies, we need to rethink the entire system in the end, how we design them. We have also published a lot of work in this area. I'm going to describe some of these works, but not many of them actually. But industry also, Intel come up with this theme in 2019. Intel obtained persistent memory. It's actually very similar to this technology, 3DEXPOINT, is somewhat similar to PCM. I'm not sure if you can still buy this theme because Intel has discontinued this line because of probably unsuccessful business, plans. But to me, that doesn't mean that this technology is a bad technology. I mean, still people can work on it. And there are actually a lot of interesting papers that people use these themes in their, basically they put these themes in their system and then develop libraries for persistent memory. And they basically show how important, how they can be useful for those applications that they need persistent data essentially. But yeah, maybe you can find these themes and buy them, but probably they are also very expensive. Does any of you have it or no? Yeah, I don't know actually how much is it. In the past that they were also available, they were quite expensive, but now that they are also not very available, yeah, it might be very expensive also. Okay. I'm gonna describe actually some papers that we look into here. We discussed about how we can use phase change memory as main memory in this paper in 2009, and some other also papers in that time. So to conclude, charge memory, like DRAM and flash, basically you write data by capturing charge in the capacitor or in the floating gate, and then you read data by detecting the voltage, essentially. However, in resistive memory, which can be a PCM, STT-MRAM, memory store, I will have a slide about them as well later, you write data by pulsing current, and then you read data by detecting the resistive R in that cell, essentially. So there are several promising resistive memory technology. This is actually not exhaustive list. People have been developed a lot, and people are developing also. And like there are time to time, actually, we have some communication with some companies, some startup that they come up with some new emerging memory technologies, and they want to test it, to see how they work. Because sometimes, they specifically also people from the device level, they work a lot and they come up with the memory technology, which can be, for example, one cell or two, something like that. They have a prototype of that. And they basically characterize that prototype and they come up with some numbers, and these numbers seem reasonable. But how basically we can expand that one cell to a memory array? Because in the end, memory should be an array. You don't make cells completely separately. You need to combine them to make an array. So how do you design the whole array? Actually, is a big question. And that's basically the part that usually researchers at the architecture level, system level, they actually come to play here. I mean, we do a lot of research here. How you can actually combine and make an array? What would be the essentially the integration technologies? How you place, for example, row buffers? I don't know, where do you put a sense amplifier or other sensing technologies that you have? Like there are a lot of architecture level decisions that you should make here in order to make these technologies. And that's why simulation is very important for us. Without simulation, you cannot really test any of these ideas. But yeah, good that we have simulators. So PCM is actually you essentially inject current to change material phase. And that's basically change the resistive value of the material. Another technology is STT-MRAM, which I will also show. I have some slides about that as well. Essentially, we inject current to change the polarity of the magnet. So there's a small magnet, like I don't know, in nanoscale or micro scale, let's say, like, and then you essentially, when you inject current, you can change the polarity of that magnet. And then based on that polarity, you can define the resistive of that STT-MRAM. There are also other technologies like memory store, RRAM, ReRAM, which they essentially, when you inject current, we change the atomic structure, and then resistive determined by atom distance, like how far these atoms are together, depending on the structure that you have. I'm not going to detail of memory store, but you can also search and read about them. We will see actually much more first about PCM. So phase change material, which is essentially this chalconite glass, exists in two states. Amorphous, which is a low optical reflexivity and high electrical resistivity, essentially. And crystalline, which is a high optical reflexivity and low electrical resistivity. So from the optical, actually, a difference between optical, that's why actually this architecture has been used in rewritable CDs in the past. But nowadays, also people come up with the circuitry that they can define the electrical resistivity of this phase change memory and how to change it, that resistivity by basically by the right circuitry, essentially. So PCM is a resistive memory, and so you can encode high resistance as 0 and low resistance as 1. And PCM cell can be switched between states reliably and quickly. It's not very quick compared to DRAM, but still it's faster compared to, for example, flash memory. So how does a PCM work? Very briefly, when we want to, so we have two different states, write and read. When we want to write, essentially we change the phase via current injection. So you essentially, depending if you want to set this, the PCM into crystalline phase. So that's the operation, we call it set. So we need to sustain a current above basically that. So when you apply a current, that increase the temperature of the material, So you need to apply enough current and you keep that current actually steady such that the temperature of the material actually is above the temperature, which we call it the temperature of crystalline. And so you keep it for some time, and then at some point you basically you leave it. And so with that, you can actually change, set the phase to crystalline of the PCM. However, in order to reset it, actually you apply quite high current, which means that it increases the temperature actually above a melting temperature. And then after some time, which must be actually quite shorter, you quench it. And with that, you can actually move to amorphous state of the PCM. So the thing is that these temperatures actually are not really low. They're quite high. And that's one of the big reasons that why these architectures are very hard to develop. In the past, actually, there are some numbers that, for example, they say that the right temperature is somewhat around, I don't know, 600 Celsius, which is a lot. Like when you apply that temperature, that has a lot of bad effect on other connections of that cell, and that can actually cause low reliability of the cell. But a lot of vendors and also academia people work on it, and they come up with different techniques, such that they can reduce the temperature. I don't know exactly how they fix it, but temperature is not that bad. But it's still, you need to apply high temperature in order to change the phase. When you want to read, actually, you need to detect the phase via material resistance. So essentially, depending on basically the phase, whether you're in a crystalline or amorphous. So in the crystalline, you have low resistance. So when you apply a voltage, basically you have large current coming from, passing through this resistance. And by sensing the amount of that current, actually you can understand, what's the status. So essentially you need to, in the end, understand what's the resistive value stored in that cell. And with that, you can actually think of applying a voltage and then check the current. If by applying the same voltage, you get quite high current, that means that essentially that cell is in the crystalline phase. Whereas if you get a very, whereas if you get a low current, that means that the resistance of that cell is actually high, and then you are in the amorphous phase. So this way you can actually encode it on set and reset, like 1 or 0, for example, but you can also encode it in the, more bits, like, but with that, actually, you need to have a much more, let's say, detailed and accurate reading circuitry. Okay, so these numbers of, these values are actually quite old from this, some IBM paper back then. But you can actually also check nowadays prototypes for getting much, more up-to-date numbers. But what you can see here actually is that the difference between these values are actually quite large. And that's key. That's the key here in order to reliably differentiate between these low resistance and high resistance. So you can see that, for example, these numbers, we have at least 3 orders of magnitude difference, which is very critical here to, to do this operation reliably. Okay. Question? Yes.
Since we require such a high so considering that we have an array of these, then in that case, it will be a bigger issue for the neighboring cells. We try to set or reset one cell, but then because of the problem.
Yes. Of course. Yeah.
Then it becomes a bigger problem as because in DRAM at least we are affecting the single column or something.
Yeah, of course. Yeah. I mean, but so that's an issue. I agree. But I know that also like vendors like Intel in Optane SSD, they also have Optane SSD that they use the same technology for SSD. But for this Optane DIMM, they somehow fix that temperature issue. So they don't warm up the cell that high. Actually, that's going to be very bad if we warm up to, I don't know, 600 degrees, just impossible. But yeah, of course. So that's also the very good point that you mentioned here. These non-volatile memories, emerging memory technology, they also have some sort of read disturbance and write disturbance errors. We're going to also see in flash memory later, for example, how that can happen. But in PCM and ReRAM, STM RAM, they also have similar kind of idea, similar kind of problems. And people have looked into it, not a lot, but there are some works in that line as well. Yeah.
In a previous slide, you mentioned that this technology has the ability to scale up to 9 nanometers.
Yes.
So then that issue becomes even larger.
Of course, yeah. But overall, from the scalability, still people think that this architecture is more scalable because people, I mean, this ITRS is kind of a roadmap, that they essentially try to predict how we can go. And ITRS prediction is still consistent that PCM, for example, is more scalable than DRAM. I mean, fundamentally because you don't store charge. Yeah.
It will be more scalable than DRAM, but do they consider it to be more scalable than NAND? Because NAND scales really well compared to the.
Well, I think so, because NAND flash memory actually nowadays also they are quite error prone. If you downscale them more and more, we are developing techniques to overcome these issues, but yeah, NAND flash memory also they are not very scalable in that sense because of the storing charge essentially. We're going to see a lot actually in the flash memory lectures, a lot of errors that can happen in that architecture. Okay, any other questions?
How steep are the how steep is that?
Yeah, I don't know really detail of that. You need to check those prototype papers that people discuss about how they can apply the pulse in the end, because to cause phase changing of PCM. But yeah, I don't really know the exact detail of that pulse. Okay. So there are opportunity by using PCM. So first of all, it scales better than DRAM and flash, which of course it's arguable. We can discuss it, but overall, fundamentally, because it doesn't store charge, it's much more scalable. It requires current pulse, which scales linearly with feature size, and is also expected to scale to 9 nanometer. We have also prototype at 20 nanometer. IBM actually has been working a lot on the PCM. In Zurich also IBM Research. They have a I think it still is a prototype, but they also have a PCM array that people can use that PCM, but even for doing computation. Later on, we're gonna see that also, like processing using emerging memory technology. You can also use PCM to do processing, and through some research, essentially people can get kind of, I don't know how easily, but people can get access to run, for example, some neural networks, on PCM array. So IBM has been working a lot on that. And actually IBM was one of the company that they also write several papers in that line of scalability challenges of DRAM in 2002 or so. There are interesting papers from IBM in that line as well, which I encourage you to check. So PCM can be denser than DRAM because the fact that we can store multiple bits per cell, and also because we can scale it more. So we have prototypes with 2 bits per cell and also 4 bits per cell in different years. It's also non-volatile, which is we can retain data for more than 10 years at 85 degrees. I mean, this is a kind of a report from prior work, which means that we don't need to also, at the same time, also we don't need to refresh. And that's why we have low idle power in this architecture. So these are good things. I mean, this is all we already discussed. So for cell resistance, at the high level, you think of multi-level cell that you can chunk it in more windows. So here you are storing 2 bits, for example, per cell. However, when you have less margin between values, we need more precise sensing modification of cell contents, which in the end, it will cause a higher latency, higher energy, as well as also lower reliability. So we have essentially this capacity and capacity performance trade-off here when we go to MLC PC. Okay, so when we wanted actually to work on this topic to see how we can use phase change memory to make potentially to see the position of that memory, can it be a replacement of the DRAM, or should be augmented to DRAM? So we wanted to know about the numbers and characteristics of this architecture. So essentially, we surveyed a lot of prototypes from the year between 2003 and 2008 from different industries as well as academia that publish in actually some different conferences, journals like Electronic and Device Meeting, VLSI, ITRS, and Circuit Designs. And in the end, we try to basically come up with some parameters which we can use to to simulate this memory. So here is a table that we report in this paper, and you can see that from different prototypes that they have been published in different years from 2003 to 2008. And here also we are reporting essentially different characteristics of that. So the problem is that one big important takeaway message here is that we don't know a lot about this technology. So it's very hard to understand what's going on, because in many of these, some of these actually prototype, the amount of information that has been reported is actually very little. Like this architecture in 2003, we know the material that they used, and also how the set time, the set current, reset time, and also the reset current. And also we know this about write endurance. That's another unfortunate thing about these memories, which you cannot essentially this architecture can afford limited number of writes. So here in this architecture, PCM, if you write, for example, more than 10 to the power 7 to one cell, essentially your cell cannot do read and write properly. It might be low reliable, or it might be completely dead, depending on the the technology. But many of these emerging memory technology, they actually unfortunately have this write endurance problem, which in the end limits the lifetime of the system. And a lot of research actually also has been going on in order to come up with a solution, not to improve the endurance, because it's, I mean, also it's good to improve the endurance, but that's might be very hard because it's very fundamental to the architecture, and people try to actually improve it. But also people try to develop a lot of techniques at the high level, at the architecture level, at the software layer, in order to improve the endurance, improve the lifetime. For example, think about a memory. If you just write to one location of PCM memory, then you're gonna wear out very quickly. Whereas if you can balance the writes, then you can do using some wear leveling techniques that you try to level the wear out of the whole memory. That can potentially increase the lifetime within that endurance problem. But I'm gonna show you some numbers later with PCM, which in the end, this actually is very fundamental issue and it's very hard to handle. So it's very, a lot of things needs to be done in this line. Another issue here is that these numbers are quite different, depending on the material that they use, depending on the circuit, sensing circuitry that they come up with. So essentially we have many different numbers also. So it's very hard to reason about it, and then come up with some set of numbers that you can do your simulation based on it. But again, another point, I want to repeat my point here that when you work on emerging memory technologies, that's always the case. You don't know a lot about it, but still people should try to do research using whatever we have, and then come up with some techniques, because these techniques and architectural techniques that people generate provide valuable insights that can be used actually for other technologies as well. So it's very important to continue research in this line as much as possible. So we work on these numbers, and then we come up with some numbers, which I'm going to show you later. But basically our point would be, we wanted to see where can PCM fit in the system. So we have caches, main memory, which is DRAM, and then we have a storage, which is solid state drives and on hard disk drive. So here in the grand scheme of things, you can see that in this scale, we are reporting the essentially typical access latency in terms of processor cycles for a 4 gigahertz processor. So these are a number of cycles, like accessing L1 cache SRAM can take 2 processor cycles essentially. Or last level cache, for example, if you use EDRAM, is going to take 2 to the power 5, like 32 cycles essentially. And DRAM actually locates around here, and we have flash memory and hard drive. So you can see that actually, like for flash memory, the location was actually very clear. It cannot replace DRAM, but it's a very good, architecture that can be combined with hard drive, such that you try to address most of the requests through the flash memory, which in the end you're going to get much lower latency compared to hard drive. But still, there is also good in some systems that you have also hard drive for some data that you don't need them frequently, essentially. But for PCM also, we need to understand, for other emerging memory technology, we also need to know. So PCM latency is actually somewhat close to DRAM, but still worse than DRAM, but much better than flash memory. So whether or not it makes sense to have PCM in this hierarchy, that's a big question. If PCM can replace DRAM completely, then okay, we have a PCM here, and then flash, and then hard drive, which might be good. But then it would come at price of performance overhead, which it's not clear how we can overcome these issues. So that's essentially the problem, the high-level problem that we wanted to work on it through these works to see where we can actually put this memory on the grand scheme of this memory. So using our basically literature or server review, we come up with these numbers that read latency of PCM is around 50 nanosecond, I mean back then, which is 4 times slower than DRAM, however, much faster than NAND flash memory. Write latency is around 150 nanosecond, which is 12 times longer than DRAM, but it still is actually much faster than NAND flash memory. Like we didn't report here, but NAND flash memory write latency is something around 100 microsecond, which you can see clearly the difference here that PCM is much faster. Write bandwidth is essentially 0.1 times of DRAM, which shows we have much lower write bandwidth, but still we are similar with NAND flash memory. Dynamic energy, specifically also for read, I think we have 2 times higher read energy compared to DRAM. For write, we have 43 times higher energy. And dynamic energy is also very similar to NAND flash memory. Endurance, so writes induce phase change at 650 degree, which, as I said, I mean, this has been kind of solved in some new architectures. And that high temperature actually cause basically contacts degrade from thermal expansion and contraction. So that basically high temperature, low temperature, all these things would cause that this architecture cannot tolerate more than 10 to the power 8 writes per cell. Whereas for DRAM, actually, no one has reported endurance problem. So we can ideally think that DRAM never wear out. But for NAND flash memory, actually, they wear out much quicker. Like in NAND flash memory, it can be somewhat around 10 to the power 4 or 5, something around that. And the cell size is also from that node that we tested, actually, it's larger than DRAM. And it's also larger than NAND flash memory, but it will scale with feature size and also using multiple level set. So the takeaway here is that when you work with phase change memory, there are a lot of rates. But essentially, we wanted to see if we can, make it somehow, available and useful for these systems. So at the high level, at the architecture level, we can think of some pros and cons. So pros over DRAM is that better technology scaling. So capacity and costs are better. And it's also non-volatile, which can memory. We discussed a bit about it. And it also has a low idle power. So we don't have refresh. But at the same time, it provides higher latencies, higher active energy, lower endurance, and reliability issues. I'm not going to discuss about it a lot, but this is also another issue that we can have resistance drift during the time. So these, for example, PCM resistives can actually drift, which means that you need to update your reference resistance, essentially, or your reference voltage, in order to keep reading from that memory reliably. And at some point, you may need to actually refresh it also. Kind of, you can think of refreshing as a, because after some time, it's true that these technologies are non-volatile and they can retain the value for a long time, but that basically resistance drift actually can cause that at some point you need to get back to the normal range, so meaning that you might need to rewrite essentially, which means kind of refresh. We're going to see that actually in flash memory, for example, a lot. So then there are a lot of challenges in enabling PCM as DRAM replacement or helper. So we want to mitigate PCM shortcomings and find the right way to place PCM in the system. Okay. I think now is a good time to take a break. Let's be back at 2:15 and we will continue with that. Yes.
So if you have, let's say we are activating one node,
Mm-hmm.
and there are some other data retention to have.
Mm-hmm.
But if you also make a we are just creating another backup sort of a thing.
Mhm. Yeah, potentially, yes. You're thinking of in the line of using PCM as a helper of DRAM, which I'm going to discuss some techniques in that line, but this can be also potentially can be considered. Of course, the problem here is that how frequently you need to update your copy, you know. So yeah, that might not be, because one way of using DRAM and PCM together is that you try to capture many of these, let's say, frequently accessed data, like those that you're going to write a lot or read from them a lot, keep them in DRAM, and then less frequently accessed data in the PCM, for example. You know, that's one idea. So if you want to have this kind of a PCM and DRAM together, and then use PCM capturing copies of DRAM, I mean, we need to think about it. I think, yeah, there are challenges, of course, but yeah, potentially we can discuss it. Yeah. Okay. Yes. Yes.
Why not think of it as a replacement?
We didn't work on it much because to us it was easier. So we wanted to solve a harder problem, essentially, you know. Yeah, like for example, Intel, they come up with this Optane SSD actually, long time before Optane DIMM, and that Optane SSD, I think, is still actually is available, if I'm not mistaken. But yeah, people can buy Optane SSD, and that's much faster. But still, the cost is not comparable to flash memory. So I think, yeah, we have also long journey in order to use PCM for that. Yeah, very good question. But yeah. Okay. Now let's take shorter break, I guess. But no, let's get back at 2:20. Let's take our 15-minute break, and we will see. Okay, let's continue. So yeah, basically we wanted to see how we can integrate PCM in the memory system of our computer system. Here is our traditional conventional system. We have a CPU and memory controller, and then we have DRAMs, right? So one way would be considering as PCM and DRAM in a hybrid memory. Then the question is that how you're managing this hybrid memory with different characteristics. Actually that seems more reasonable, to think about PCM in a hybrid memory with DRAM. This can be also kind of a DRAM can be considered as a cache for your PCM. So the main memory can be PCM, and then you use DRAM as a cache for PCM. Or it can be also, as I said, hybrid memory, which they are also part of the physical memory address space. But we didn't want to start with that. We actually wanted to start with the most aggressive thing, to just try to replace DRAM fully with PCM and see how it works, essentially, And it's not a rocket science. I mean, when you put something that slow as a DRAM, you're going to see performance overhead. But then the question is that how much you can overcome these overheads by better architecture of a memory when you're using PCM. So yeah, this hybrid PCM and DRAM, I'm gonna discuss them later, but I will start with the pure PCM main memory, which sounds more aggressive, and it's always also good to be aggressive because that can also push the boundaries, of the research. So yeah, so basically we did this initial study to replace DRAM with PCM, and using our survey, we come up with some, we consider some latency numbers or some parameters. For density, we assume that actually the density is 1.5 times of DRAM, and which is more dense. And for the latency, in this work, actually, we didn't benefit from higher density of this architecture. We did actually more pessimistic research. That's a good thing that we know that we can benefit from that. When you have a denser memory technology, potentially you can have larger capacity. And when you have a larger capacity memory, potentially you're going to the disk, less frequently, and that comes with performance improvement, and energy improvement. But we didn't want to, we didn't look into that also. We tried actually to be very, very pessimistic. So it's only, so we have all the bad things here. Latency is longer, read latency and write latency, 4 times and 12 times of DRAM, respectively. And we have also limited endurance and high energy consumption compared to DRAM. So these are the numbers that we developed. We implement them in our simulator. That's the beauty of having simulators, that we can use a simulator that simulates DRAM, but then you can change some numbers, timing of that DRAM to essentially model PCM. So in the system with 4 core and 4 megabyte L2 system, and also the same organization of DRAM, like row buffers, banks, and peripherals, everything is similar as DRAM in this simulation. The only differences are the numbers, latency numbers, and energy numbers of this memory. So we observe that on average, we have 1.6 times delay, longer execution time, 2.2 times energy consumption, and 500-hour average lifetime, which sounds terrible, right? Specifically this lifetime, I think we don't want our system to die, after 500 hours. And remember that this is an average lifetime. So in some cases, actually, for some application, actually lifetime is much lower. So that was kind of expected, but if you just purely or naively replace DRAM with PCM, here are the numbers that you can get. Long execution time, huge overhead in execution time, huge overhead in energy consumption, and huge overhead in the lifetime of the system. But now the question in this work is that, can we overcome these challenges by some architectural solutions? So we tested different ideas here. One idea we use, for example, we use multiple narrow row buffers in each PCM chip. So remember that in DRAM, actually read is destructive, right? So when you basically access a row, you move that row in the whole sense amplifier, which that sense amplifier should be large enough for the whole row. And you need to keep that sense amplifier actually active in order to recover from that destruction happen when you're reading, right? However, PCM read circuitry is actually not destructive. So you don't really need that long row buffer. So you can actually use a much smaller sense amplifier. And then you gain some area. And with that area, you can actually add some buffers vertically. So here, these buffers, actually, you can fill it up with different rows. Whereas here, actually, you have different data from basically different columns of one row in DRAM. But here, you can actually have several, let's say, columns, but from different rows. And with that, actually, you can provide, you can keep data more, essentially, in your latches and try to access as much as possible through this buffer. Like you have a kind of you're using this row buffer as a small cache that here you have. So that provides actually better endurance, because when you also want to write, you don't necessarily write to PCM, you essentially write to latches. And when you have to close that latch, essentially, you need to write in the end to PCM. And that also provides better latency, because you write only to the latches, or you read from latches, and also better energy consumption. Of course, at some point, you need to write to the PCM, but you can also think of that doing it at the background, right? So you have a basically write buffer, and so somehow you need to manage the size of that row buffer, that write buffer. So as you write in that write buffer, you are actually filling it up. But when you are actually very close to have it full, there might be some operations going on at the background, saying that, okay, I'm gonna empty this write buffer. So you try to write something at the background to the PCM such that you make some spaces essentially in that write buffer, right? So you can actually try to hide some of these write latency actually in the background operations. And that's the beauty of using kind of a write buffer for such things. Make sense? So that's one idea. Another idea which we use here is that we write into array at the cache block or word granularity. We don't write at the whole, row buffer. Like in DRAM, what's happening here is that when you want to write, you update the row buffer, and that row buffer is open, and you need to wait for that write recovery, write restoration, such that you write the whole row buffer into the DRAM row, right? But here in PCM, actually, you can write in much lower granularity. You can write only at word, for example. You don't need to write at the whole row of the PCM array. We didn't push it more, but there are actually works later on, like Samsung, for example. They come up with the idea of, for example, whenever we want to write, we read first and we compare, and we only write those bits that they are different. Because here we really want to reduce the number of writes, right? So very important to only write for those cells that they really need to, change. So you can actually also do much more. So this actually, the second idea helps a lot to reduce unnecessary wear out. So you can potentially increase the lifetime of the design. Make sense? Yes. Yeah, but it's similar to this sense amplifier buffer. So we don't necessarily increase the total area. So this structure, you can, instead of having one big structure horizontally, you can think of having the same area actually vertically, So you don't necessarily actually increase that buffers, right? Yeah. So in DRAM, actually, your sense amplifier is also the buffer, right? But in PCM, actually, the sense circuitry is a bit different. You're using another sense circuitry, but then you can use, you gain some area, and then with that area, you can use it for adding some latches or buffer here vertically. There are some area analysis in the paper, but in the end, it doesn't really increase much area compared to the DRAM architecture. Okay. Question? Okay. So with these techniques, we basically improve a lot. So the execution time has been degraded by only 20% now on average. Energy consumption is overall the same now on average. And the average lifetime is now 5.6 years. But again, it's average. You can see that there are some applications that the lifetime is actually still quite low. So there are some caveats here. That the first caveat is that worst case lifetime is much shorter, so there is no guarantee. So potentially there can be also some malicious program, that try to write a lot in this memory and wear out your memory fast, So now you can also think of some security attack, to target the lifetime of your system by writing a lot to your phase change memory, for example. So that's the thing. So we don't provide guarantee in the lifetime. In normal cases, the lifetime on average is good, for example. Another caveat here is that intensive applications see large performance and energy hits, which again is important to think about it. And also, are we using optimistic PCM parameters? So we didn't know a lot about what are PCM parameters, and we try to we try to set these parameters based on the prior reports, but still it's good to know, are these numbers are optimistic or pessimistic? Later on, by seeing numbers from Intel Optane also, it turns out actually our numbers were not that off. They were okay, but of course, we can also rethink about it. Also, all the results here, I would say that we can, get everything with a grain of salt, essentially, because of the models that we have, like this energy model. Like we have used some energy modeling, which we did our best, but of course it's always hard to do by modeling energy. So the trend is okay, but essentially I think if we need to probably there is a value to do this research again now also, because we have much more accurate models, and we know a lot more now about PCM prototypes. There are much more in the market, not in the market like through the academia works and industry. So we can potentially, change these, tune our simulations better and redo all these experiments. But I think the high-level takeaway message here is that by using some architectural techniques, we are able to overcome some of the challenges of PCM, of course, but still, it's very hard, for example, in the lifetime of the PCM. So it's very hard to guarantee that your PCM is not going to wear out, for example. Or still also you're observing some performance overheads. And some applications actually, like for example, this application, FFT, we are observing still 60% execution time latency, right? So as a takeaway, again, it's very hard to completely replace DRAM with PCM. Okay. If you want to learn more, there's a paper that you can check. It's going to be also part of optional reading or required reading. So we're going to see later, but this paper is going to be one of the reading also. And this also the IEEE micro version of this paper, which is a kind of a shorter. Okay, and this idea actually also, as I said, Intel Optane memory, they have developed it in 2019. Basically, so this can be also used in. So now you can actually test such ideas of PCM actually in real life as well. Assuming you have this DIMM, you can just put this DIMM in your computer, and then you can essentially, execute. You don't need to simulate here, for example. If you want to sweep the parameters of PCM and see how it goes, yes, you need to use simulator. If you want to change the memory architecture and see how it can improve, yes, you need to use the simulator. But if you want to just use the numbers from this device and see how they can work in real life, how performance overhead, and also potentially develop some libraries in the line of persistent memory, you can easily use that essentially in real execution. Okay. So let me also quickly go over this paper as well. It's a kind of a short discussion, but essentially in PCM, some PCM bits, when we store several bits in one PCM cell, some PCM bits take longer to read. And it's actually, I have a good actually kind of picture here. Let me get to that. Yeah, here. So, so we have essentially read asymmetry. So we start with initial voltage, fully charged capacitor. That's the read circuitry that we have. So you basically you have a capacitor that you fully charge it. Maybe actually it's good to show it because one of you asked how we can read, and this is actually one of the read circuitry here. So you have essentially we have a capacitor that we fill with reference voltage, and then we connect this capacitor with our PCM cell, right? And depending on the resistance of this PCM cell, we have a RC delay, right? How fast we are draining charge from that capacitor. And then you actually calculate this latency, and based on that, you can understand, okay, basically what was stored in that PCM cell. And that's one way of doing that, essentially. Okay, so the problem is that here we have read asymmetry. You can see that if we want to, so when we set the voltage at high for this fully charged capacitor, and then we connect it to the PCM, essentially the charge and the voltage of that capacitor is drained. But depending on the position, you know, so what we have already stored in that PCM, you're going to have different latency. So it will take longer time to read 0, 1, for example, right? Or for example, if you have a store 0, 0, then you need to spend longer time. So that's the read asymmetry that we have in PCM. Make sense? But however, the thing is that in existing devices, both MLC bits are read at the same time. So we need to wait maximum time to read both bits. However, we can infer information about bit 1 before this time. So if you check this, you know, this window, you can see that MSB, like here is 1 and here is 0, for example, right? So for these two, we have MSB most significant bit are 0, and here most significant bit is 1. So essentially, you can potentially read the value of bit 1 faster, right? But time to determine the bit's 0 value actually takes longer time, right? So that's the thing you can use up. For example, you can think of, okay, I'm gonna store 1 page at MSB. So you don't need to use, when you have an MLC, you don't need to store the 1 page in that, you know, like different bits of that page in different bits of MLC. You can think of, okay, I have in MLC that I store 2 bits per cell. I'm storing 2 pages, 1 page at MSB and 1 page at LSB. And with that idea, the page that you're storing at MSB, you can access it faster. Okay, and that gives you some, you know, idea how to locate your data, how to map your data. For example, you can say that, oh, this data, I need to access it much faster, so I will store it at the most significant bit page, essentially. Okay, makes sense? Yeah, that's the idea overall here. And in this paper, actually, we also look into, you know, how long does it take to transit from different states. So you can also check this if you're interested. But yeah, that's the idea, that you can benefit from these different latency, this latency asymmetric that you have, and that can give you better data mapping and buffering techniques, potentially improving performance. Does the high level idea make sense to you? Okay. Question. Now we want to change gear a little bit, go to STM-RAM. We will get back to PCM as well again, but more in the line of using PCM in a hybrid manner. But we also wanted to see how we can use STM-RAM or STM-RAM as main memory, because these memory technology is a bit faster than PCM. So STM-RAM, there is this magnetic tunnel junction MTJ device, and so that's and then we also, so this MTJ has a reference layer, which is a fixed magnetic orientation, like this reference layer. So the polarity of that magnet is fixed, and there is also another layer in MTJ, which is a free layer, which by applying the current you can change the polarity. And depending on the fact that this free layer is parallel to the reference layer or anti-parallel, you can essentially get different resistance from that STM-RAM. So magnetic orientation of the free layer determines logical state of the device, high versus low resistance. And so when we want to write, we push large current through MTJ to change orientation of free layer. And in order, when we want to read, we essentially sense current flow, similar to PCM in the end. That read circuit is not very different, because whatever happened in the MTJ, we have some resistance, you know, and in the end we want to assess that resistance. So you can think of read circuitry actually is not very different between STM-RAM and PC. Question? Okay. So there are, again, STM-RAM also has some pros and cons. So the pros over DRAM is that it has better technology scaling again. So we have better capacity and cost, is non-volatile, and low idle power. So, but similarly, it also had some cons like higher write latency, higher write energy, poor density, at least you know, at the time that we were doing research. I think still also STM-RAM latency density is not very much. So people actually now look at STM-RAM more as a replacement of caches, not DRAM. So because latencies of STM-RAM actually has been improved quite a lot. And also there is interesting trade-off in STM-RAM that people can trade off non-volatility for lower write latency and energy. So when you reduce it, sorry, when you reduce the size of this MTJ, you can actually increase, you are reducing the retention time. At some point, you really need to do refresh. But the good thing is that then you have much lower latency and lower energy consumption. So for the memory structure that you frequently access, like caches, for example, you know, you can actually play with this trade-off a lot, right? Or for example, some buffers. There are a lot of works that people try to use STM-RAM as a combination of SRAM caches or as a complete replacement of caches. There are also some works people try to use different configuration of STM-RAM as a high capacity and low capacity cache. For example, you can have a STM-RAM with a large MTJ, and that can be your, for example, last level cache, which is high capacity and non-volatile. But at the same time, we also consider one high and low latency cache beside that, or for example, the L2 layer. And that cache can be, for example, you can use MTJ. So you can make that MTJ of that cache smaller, which give you better latency and better energy consumption. But then the problem is non-volatility. I mean, at some point, like you don't need to refresh it every 64 milliseconds, for example, or every 32, but you need to refresh it. And at some point, actually, it can go crazy. So there are a lot of interesting results in some papers that people try to play with that trade-off, how frequently we need to refresh STM-RAM memory. Okay, yeah, so also STM-RAM is still, reliability of that is still questionable. So it's not that reliable as PCM, but people are working on it, but still PCM seems more reliable, at least from the prototypes. Okay. So we essentially, similarly also with STM, with the research we have done with PCM, we also did with STM-RAM. So we essentially completely replaced main memory with STM-RAM. And then we try to also improve some, improve the architecture, similar ideas, for example. And then we get some results, essentially. So the thing is that since STT-MRAM is not that bad compared to PCM, the performance overhead is very actually low. Like we have around 6% performance loss. And even so, we have actually 60% energy savings compared to DRAM. So STT-MRAM actually provides better energy savings for us. Yeah, so basically using STT-MRAM as a main memory, there is no much question, let's say, that needs to be solved much, at least from what I can see here, you know, from the architecture side. There are a lot of problems in how reliably you can use STT-MRAM, like that, the physical layer, and also density of STT-MRAM is not that dense compared to DRAM. And that's why, as I said, people think about using STT-MRAM as a replacement of cache, and that makes more sense because SRAM is actually quite large, and STT-MRAM is denser compared to SRAM memory. So you can think of, then you have a hard problem to solve. You know, if you want to use STT-MRAM as a DRAM, there is not much problem to solve. You know, it's a matter of if whether or not we want to pay that cost, because STT-MRAM is more costly, I mean, at least from now, and also density is also not that good. But as a replacement of the caches, you have solved problem. You have challenges to solve essentially. Question? Yes. Yeah, one of the main reasons is that you don't have refresh, yeah, at all. And here also, so and the bad things of STT-MRAM, like write energy compared to DRAM, is not that bad as the PCM. So STT-MRAM higher write energy compared to DRAM is not as bad as write energy in PCM. So the bad things is not that bad, but good things are very good. So in the end, replacing main memory with the STT-MRAM architecturally makes sense, you know, provide good performance. But of course, as I said, there are other problems here: reliability, density, cost, which needs to be also revisited. Yes, yes. So if you want to learn more about it, you can check this paper also. But now I want to look into hybrid main memory, which sounds more reasonable actually when you work with emerging memory technologies. Completely replacing them like DRAM sounds too aggressive. And so that's why using hybrid memory makes more sense. So this is the picture that we have shown actually before also. This can actually happen in many cases that you have hybrid memory systems. You can have different actually kind of DRAM design. You can have a slow DRAM design, fast DRAM design with different characterization. But here you can also think of, I have a DRAM which is fast and durable, however small, leaky, volatile, and high cost. At the same time, I have phase change memory or some other memory technologies, which is large, non-volatile, low cost. However, it's slow, it wears out, and high active energy, right? So, and now the question is that how you're managing your hybrid memory system here. I'm going to discuss some techniques, but this actually is still also an ongoing research direction. You can also potentially think of using some machine learning technique, you know, to optimize this hybrid memory system. In Safari, for example, we have worked a lot on using machine learning for hybrid storage when you have different storage devices. But you can also think of potentially using machine learning for hybrid memory systems as well. Make sense? Okay. So we essentially need to come up with some hardware software techniques for data allocation and movement to achieve the best of multiple technologies. Like the main question is that where to place and where to migrate and when to migrate. So essentially placement and data placement and data migration is a big challenge that you need to overcome in a hybrid memory architectures. So providing the best of multiple metrics with multiple memory technologies in a heterogeneous, configurable, programmable memory systems. And there are a lot of issues here that essentially, like design space is actually quite large. So whether or not you're dealing with your architecture as a cache or main memory. So here, for example, in our example, DRAM can be considered as a cache for phase change memory, right? Or you can also think of, okay, PCM and cache both all together, they are part of a physical memory address space, right? So that's one question that we need to answer essentially. Another one is granularity of data move and management. So are you going to do it fine grain or coarse grain? Hardware versus hardware software cooperations. When to migrate data and how to design a scalable and efficient large cache, for example. Like if we have DRAM as a cache, now the problem is that, I mean, usually our caches are not that big, right? So the tag array metadata is still an overhead, but it's not that much overhead. Like with a few megabyte or tens of megabyte of caches, that's not a big problem. But think about having 32 gigabytes of memory as cache. If you want to deal with that cache as a similar as way you're dealing with your SRAM cache, then you have problem, right? So that's why actually this part is also very interesting to look at. I'm going to discuss some very quick works in that line as well. Okay, so one option is to DRAM as a cache for PCM. PCM is a main memory, and DRAM caches memory rows and blocks. So the benefit here is that we reduce the latency on DRAM cache heat and also filter writes, which gonna provide better endurance or lifetime for the whole system. Memory controller hardware manages the DRAM cache. The benefit here is that it eliminates system software overhead. So once you have essentially DRAM and PCM in a hybrid memory structure, and that they are sharing, or they are building the whole physical memory address space, now the system software also needs to deal with that, right? Where to locate pages essentially. But once you are using DRAM as a cache, then at least system software does not need to do anything about that. So you still have a memory that system software needs to deal with that only, and DRAM is the only cache which is handled by memory controller essentially. But there are three issues here. One, what data should be placed in DRAM versus kept in PCM? What is the granularity of data movement, and how to design a low-cost hardware managed DRAM cache? So there are two idea directions that I'm gonna discuss them actually. One is locality-aware data placement, and another one is chip tag stores and dynamic granularity. We're gonna see both of them actually in a bit. So DRAM as a cache for PCM, more specifically, so we achieve the best of both DRAM and PCM or NVM. It minimizes amounts of DRAM without sacrificing performance and endurance. So essentially, you have flash memory, or let's say solid state drives or HDD, and then it's actually basically, PCM main memory is connected to your flash or HDD. And then you have a DRAM buffer here, which acts as a cache, right? Then you can actually have some potentially management idea here, how to use this architecture. So you can think of, exactly. I wanted to talk about this stuff. So you can think of a lazy write, for example, idea that pages from disk installed only in DRAM, not PCM. So you first put actually pages in DRAM and not PCM. And then you move that page from DRAM to PCM if it makes sense, for example, right? So that's a lazy write. You don't immediately write pages in your phase change memory, main memory. That's one idea. Another idea is partial writes. So we only, only dirty lines from DRAM page are written back to the PCM main memory. And that's also, you can think of, we also use this idea in other works as well. Another idea would be page bypass. So we can discard pages with poor reuse on DRAM eviction. So when you're evicting a page from DRAM buffer, you don't necessarily write it to the PCM main memory, right? If they basically reuse of that page is actually poor. So maybe it doesn't make sense to keep that page. So I'm not going to pay the overhead of writing that page in the PCM main memory. I'm going to just write it back to the flash memory or the HDD. So you can think of many, many different ideas like that, that you manage this system in order to improve performance and endurance and lifetime of the whole architecture. So with that kind of idea, we tested with a system with 16 cores, 8 GB DRAM in memory at 320 cycles, like the latency of DRAM in memory access. And in that system, we also consider we have a HDD with 2 milliseconds and a flash memory which accessed by 32 microseconds. Also, we consider that we have a flash hit rate of 99%. Meaning that when you get to the flash memory, in 99% of the cases, you find your page that you're looking at the flash. But there might be some 1% that you miss in the flash memory and you need to go to the hard disk drive. Okay, so that's a part of the analytic way of also looking at it in this experiment. And we also make some assumptions, like we consider PCM is 4 times denser and 4 times slower than DRAM. So that's also another assumption here. And DRAM block size similar to PCM page size, 4 kilobyte. 4 kilobyte. Okay. So we tested actually different baselines. 8 GB DRAM is the baseline, and also this 32 GB DRAM, which is the kind of idealized system, right? So we want to see basically the baseline is 8 GB. Ideally, we want to have 32 GB of memory. So if we consider that 32 GB DRAM, what would be the performance? That gives us the gap, essentially. And another design point could be 32 GB PCM, that you use PCM to replace DRAM fully, right, here. And another design point could be 32 GB of PCM plus 1 GB DRAM as a cache or write buffer for you. So these are 4 baselines that we are comparing here. So you can see that actually even using 32 GB PCM actually provides better performance compared to 8 GB DRAM. The main reason, even though PCM is much slower, the main reason is actually because of the higher capacity. It provides less frequent access to the flash memory and also the hard disk drive. So, which is something that we didn't consider in our prior work. So in the prior work that I showed you, that we replaced DRAM completely with PCM, we didn't benefit from the higher capacity of the PCM, right? But here we are saying that if I use a higher capacity PCM, so I will access flash memory and also hard disk drive less frequently because you have a larger memory, right? Then that can actually potentially provide better performance for you. Okay, so that's a good thing. And however, more interestingly, actually, using 32 GB PCM plus 1 GB DRAM as a cache gives you actually relatively similar performance as using the 32 GB DRAM. Okay, so that's a very nice trade-off. So you can actually get almost the same performance of having 4 times larger DRAM by using 32 GB DRAM, which is roughly the same size of 8 GB DRAM because PCM is 4 times denser, at least in this assumption, which is not a wrong assumption also. Think about 1.5 times denser, and also if you use store MLC 2 bits per cell, you can get roughly to 4 times the denser PCM. So with 32 GB of PCM, you are essentially your area is still similar to 8 GB of DRAM. So you can essentially get the same performance of almost the same performance of 32 GB DRAM by using 4 times smaller memory structure, 32 GB PCM, plus 1 GB DRAM, which as a cache. Okay. So that's the beauty of using this hybrid architecture that gives us much more freedom to improve performance. And so yeah, this architecture hybrid performs similarly to similar size DRAM, significant energy savings with PCM DRAM hybrid. And average lifetime actually is also 9.7 years. But again, there is no guarantee. So I think it's very hard to also deal with this lifetime to provide good guarantee for that. Question? Yes. Is it faster? Where? 32 gigabytes PCM is always slower than. It's normal execution time. Lower the better. Yeah. Okay. So if you want to learn more, check this paper. But I think let's get another break. It's 3 p.m. For 15 minutes, and we will be back with the rest of this lecture. Okay, let's continue. I think I have 90 slides or so. So I will, but hopefully these slides are not that dense as before. So we're gonna see. So let's also discuss a little bit about the data placement in hybrid memory. So you can hear you're seeing a system with two channels. That we have two memory A and B, and A is fast and small, like for example DRAM, and memory B is large and slow, like for example PCM. And so you can have different pages in different A and B. So now it's a kind of a hybrid memory. And at some point you want to migrate actually one page from memory B to memory A. So which memory do we place each page in to maximize system performance? And then the problem also how you balance the utilization of both channels. You don't want to keep one channel completely underutilized, for example. So page migration also have performance and energy overhead because in the end it's a kind of data movement, right? So you really want to do it when it amortize the overhead. So the idea is characterize data access patterns and guide data placement in hybrid memory. So for streaming accesses, we can say that PCM is as fast as in DRAM. Because when it's streaming access, you're mostly actually servicing requests in the page buffer, right? So that's why you're not dealing with the PCM access latencies. So similarly, also in DRAM, you're servicing a lot with the row buffer, right? When you have the streaming accesses. So those applications with the streaming accesses, PCM is as good as DRAM in terms of performance. But for random accesses, DRAM is much faster because with you time to time you need to basically close the row buffer and then access the DRAM, and then DRAM is since faster than PCM, you're going to see better performance with DRAM. So the idea here is that we place random access data with some reuse in DRAM and streaming data in PCM essentially. So that's the idea of this work. Key observation is that, as we said, row hit latency is similar in DRAM and PCM because of that buffer accesses, but row miss latency is small in DRAM and large in PCM. So that's why we place data in DRAM, which is likely to miss in the row buffer, meaning that we have a more, let's say, random pattern. So that's one way. And another criteria here is that we want to have reused many times. So we cache only the data worth the movement costs and DRAM space. So for those data that we have random accesses, definitely DRAM is better. We know that. But the problem is that if the page is already stored in PCM and now you want to move it to DRAM, you want to make sure that that page at least have enough reusability, because such that you can amortize the overhead of moving data to the DRAM. So based on these two conditions, we decide and move data from PCM to DRAM essentially. And with this idea, which is RBLA dynamic, which is row buffer locality aware data placement in a dynamic way. So it provides better performance compared to PCM only. And it's also relatively similar to having a 16 gigabyte of only DRAM. So it's a nice trade-off, between having full DRAM, a nice trade-off between either having a full PCM or having full DRAM, which comes at a huge cost, So with that, you can actually provide potentially better performance, better trade-off. So that's a paper. Any question? Okay. There are some, however, these existing solutions that I discussed, for example, one of them. So they are all heuristics, and they consider only a limited part of the memory access behavior. Like, for example, they do not directly capture the overall system performance impact of data placement decisions. Like, for example, they don't capture memory level parallelism. So here is an example. Like, for example, when you have only one page and you know that, okay, I need to migrate this page for better performance. So you migrate this page to the faster memory, and then you are saving some cycles, right? However, think about it that you have 2 pages, and in an MLP, you are actually accessing these 2 pages, right? And then you if you only migrate one of these pages, then one of them is going to be accessed faster, but another one is still slow. So in the end, with MLP, you're not saving cycle here, right? So it's important that you migrate also another page and these two pages together such that you can save cycles. So this gives me an idea that migration also should be aware of MLP also, you know. But yeah, essentially, yeah, in page migration decision need to consider MLP. However, in this work cluster, which we published in 2017, we wanted to have more generalized mechanism that essentially directly estimates the performance benefit of migrating a page between any two types of memory, and places only the performance critical data in the fast memory. So it's a kind of a general solution that you can apply to any hybrid memory. So that's why we propose utility-based hybrid memory management. So a memory manager that works for any hybrid memory like DRAM, NVM, DRAM, RL DRAM, and so on and so forth. So the key idea is that for each page, we use comprehensive characteristics to calculate estimated utility. And utility, you can think of performance impact of a migrating page from one memory to the other in the system. And we migrate only pages with the highest utility. So pages that improve system performance the most when migrated. So once you have that utility numbers, then you can easily, you know, judge and then move the page with the highest utility. Of course, the question is that how accurately we can estimate the utility. So in this work, we use some performance model. We estimate utility using a performance model, and we migrate only pages with whose utility exceed the migration threshold from slow memory to fast memory. And also we periodically adjust migration threshold. So there are some things here that you can think of, like performance model, these also this threshold. So there are some factors, you know, that affecting the performance and effectiveness of this technique. But assuming that you have a good model, you can actually can calculate application stall time reduction, and how much would migrating a page benefit the performance of the application that the page belongs to. And with that, you can basically in the end see application performance. Also, you can see application performance sensitivity. Like how much does the improvement of single application's performance increase the overall system performance? Because there might be many different kernels going on or different threads. Think about the multi-thread scenario. If you increase the performance of one thread, does it affect the whole program or not, right? So that's why these two parameters are important, like how much we can reduce the stall time of that application or that thread, and how much we can improve the improving performance of that thread or application would affect the overall performance of that of the system. So once you know that, you basically you can rank them, and then you can migrate those with the highest utility essentially. So we essentially use this utility factor, which we calculated based on the stall time reduction, and we also use a weight for the sensitivity essentially. And with that, you can judge if you can move or not. But of course, you can think of using a machine learning, for example, to model it better, and also for this to get rid of these thresholds. Essentially, you know, there are a lot of thresholds going on. It's also yet another you know, example that we are using thresholds. So it's always good to think about using some machine learning techniques to do it more intelligently. Yeah, so using this utility-based technique, actually, we show that we are improving performance for different workload memory intensity category, sustainability compared to, you know, the best state of the art. Make sense? Okay. And also sensitivity to slow memory latency. We actually try to use different parameters for the slow memory, and we report the performance of this technique compared to, you know, prior works. And essentially, we show that we keep the effectiveness compared to different latencies of that. So this utility-based technique improves system performance for a wide variety of hybrid memory systems, essentially, which shows the generality of this technique, you know, that can be applied to different hybrid memory structures. Make sense? Okay. So more about this paper, sorry, cluster is actually the conference, which they call it IEEE cluster conference. The technique is actually utility-based hybrid memory. I just made a mistake in the beginning. Okay, so there are challenges and opportunity, of course, enabling an emerging technology to augment DRAM, and so how we manage these hybrid memories. Another challenge is designing effective large DRAM caches. Like once we have if we use this DRAM as a cache for that PCM, now that cache is large. So how you're managing that is a big, important question to answer. So in this example, this DRAM is a small and fast cache for the PCM, which is high capacity. So whenever you want to load, CPU sends the load instruction, essentially, we need to check this the tag array, let's say, of that DRAM to see if we have that data in our DRAM or not. If not, essentially we go to the PCM, right? So now the problem is that your heat time is actually quite large, like how you're handling that. And the metadata is going to be also huge. You know, then the overhead of that tag array is also very much. So one idea is that we can store tags in memory. So we can store tags in the same row as data in DRAM. So in the DRAM row, we have different cache blocks you can think of. And then you can also store tags allocated to this cache block also in the same DRAM row. So with that, when you access the DRAM row, you read the tag array and also with the cache block. So I store metadata in the same row as their data, and metadata can be accessed together. So benefit is that we have no on-chip tag storage overheads, but there are downsides that cache hit determined only after a DRAM access. And cache hit requires 2 DRAM accesses. So you access DRAM, you get the tag. If hits, then you need to access again DRAM to get the data because of the different columns, you know, that you have. Okay, makes sense? Good. The second idea is use cache tags in SRAM. So recall the first idea that we store all metadata in DRAM, but then in order to improve performance, we can also have a cache in on-chip SRAM to cache essentially frequently access the metadata. So you can have the original you know, structure for all metadata in the DRAM, but then you also have a cache, small cache and fast, which you can use it for, you know, frequently access data, such that if you're lucky and the data that you're accessing, you can find a tag in that small cache, then you can essentially, you know, provide better performance. So essentially, you can think of, okay, now I have a cache for metadata, right? I'm caching the metadata in a small SRAM array. Another idea that we look into this work is using dynamic data transfer granularity. So some applications benefit from caching more data. So they have a good spatial locality, others do not. So large granularity wastes the bandwidth and reduces cache utilization. So the third idea here is that essentially we have simple dynamic caching granularity policy. So it's kind of cost-benefit analysis to determine best DRAM cache block size. Remember, I think maybe we discussed in this course, I don't know, like related to the super block. Do you guys know about super block or sector cache, for example? So there are works actually that people show that there are applications that they can benefit from large cache lines, like large cache block. So they come up with this idea of a super block, and you have a big line. But the problem is that if you always you know, bring the whole cache block to the cache, then you're actually wasting a lot of memory bandwidth, and it might be not efficient. Then people try to come up with the also idea of sub-block, which you have a tag for the super block, and also you have tag for sub-block. Then you can essentially bring sub-block gradually in the cache. You can also think of having some prediction to bring some of these sub-blocks, or you can also think of having some prefetcher that brings some of these sub-blocks faster. Similar idea can also work here, that essentially you can determine base DRAM cache block size and then manage it actually dynamically, depending on the application that can benefit from it. So we group main memory into sets of rows, and different sample row sets follow different fixed caching granularities. And depending on which granularity we can benefit, we are mapping actually through different these row sets essentially. Okay, and also the rest of main memory follows the best granularity, and then cost benefit analysis which we can do here to to come up with a good trade-off between different applications. Question? Yes. Yes.
Because we'll have to run treatment to just check.
Well, if you think about having one set per one row, then you don't need to read multiple rows. No, you are thinking about fully associated cache, I guess.
Okay. Yeah.
Right.
Yeah. No, okay. So in this case, you're saying this is a
for example. Good question. Okay. Shall I move on? Question? Okay. So yeah, this work, Timber, we show that actually it provides really good performance compared to some prior work, and also better energy efficiency. How effectively we are managing the cache, this large cache, as a large cache for the PCM. So if you want to learn more, you can check this paper. It's going to be also part of reading anyway, so you can check it. But there are actually also a lot more in this line. People have worked a lot on this line of DRAM caches. In this table, which we showed in this paper, Banshee, you can actually see the different techniques like this unison, alloy, TDC. Like there are different ways of handling this DRAM cache. How we handle DRAM cache heat, how we handle DRAM cache miss, replacement traffics, replacement decision, and large page caching. So if you want to get a summary of all, I would suggest that you check this paper for the nice, actually, literature review about these works. However, in this work, Banshee, we actually try to handle it using the TLB and page table. So it's going to be actually much more clear when we talk about virtual memory. We're going to have a lecture, hopefully, for virtual memory also later, that you learn about TLBs and page tables. So if you don't know about it much, I mean, just be patient. And in that lecture, these things are going to be much more clear. But essentially, we can track presence in cache using TLB and page table. So you can use or repurpose of your TLB that you have in order to track the presence in the DRAM cache or not. So with that, you don't need to store any tag for DRAM cache, and enabled by a new lightweight lazy TLB coherence protocol. It may not make much sense now, but you're going to see more later. Once we describe virtual memory, and also once we describe coherence, we are going to have a lecture on cache coherence. And you're going to understand this work much better. But remember to look at this work later when we, provide that, literature for you later. Okay, so yeah, more, you can check this paper also if you're interested. There are also other opportunities with these emerging memory technologies. I'm going to go over them very, very quickly, actually. So one way would be merging of memory and storage, which I'm going to show that a bit later. It's very interesting, actually, this part. Because think about our today's systems, it's actually kind of a two-level system architecture, right? We have a DRAM, and then we have a solid-state drives. So the processor actually communicates with the DRAM using read and write operations, but communication with the storage is happening through the file interface, right? So why the fact that basically DRAM is very much faster, and then that storage is very much slower. Basically, this integration has been grown like that. But once we have these emerging memory technologies, we can rethink about how we want to design this memory system. Maybe we don't really need to have it separate. They can be a pool of memory which you use it nicely. We're gonna get back to that actually toward the end of today's lecture. You can also think of new applications like ultra-fast checkpointing and restorations for applications that, like for DRAM, for example, think about it, like once you have an error, it's very hard to, you need to timely do some checkpointing. But, and that checkpointing needs to happen through the disk. But once you have a PCM memory and emerging memory technology that they are non-volatile, you can potentially use your checkpointing as a persistent memory. And then that can be actually also much faster. You can also have more robust system design because it reduces data loss. And we can also do processing tightly coupled with memory, like processing using memory that we discussed. These emerging memory technologies also, they allow processing using memory. I'm going to show this one very quickly first, because I mean, we already discussed about all these things before. Like DRAM, you know that we can do a lot with DRAM, processing using DRAM. These are some works that you are all aware of that, and some lectures from past that you can check. I didn't have time to update these links to our recent lectures. I think our recent lectures in this semester is actually more state of the art. So if you want to learn more, I would say that you check the lectures that we have basically this semester. I'm going to update that for the after lecture version, but yeah. But there are also works that people show that you can use this implement similar idea like row clone and bitwise operations in PCM. Pinatubo is one of them, which I'm not going into detail of that. Also, we discussed about in our processing using memory lecture, we discussed about using these memory architectures in the crossbar array to do computation like dot product. So we discussed about, you know, the architecture of memory store, resistive RAM, phase change memory, or reciprocal RAM, that they have this crossbar array structure. And then in that crossbar, actually, you can use that to perform dot product operation using essentially analog computation capability. So we use based on this Kirchhoff's law, and with that you can actually calculate dot product. I'm not going to into it again because I think we already seen it before in the processing using the memory lecture. But yeah, so very quickly you can apply some input. So for example, you have some each of these resistance, they have some essentially conductance, right? So when you apply voltage as input, then you have a current, which is voltage times the conductance for going through each of these conductance. And then based on the Kirchhoff's law, the total current of this bit line, if you think about it, is going to be sum of all these currents. So with that, you can actually have a dot product implementation, for example. And there are actually people that they repurpose this architecture in order to use it for machine learning, for example. Like this work. So essentially, you can implement 2D convolutional kernel, essentially, using this architecture by mapping essentially your kernel filter as map them as this conductance, and then you sweep also the input to your essentially filter. And then based on that, you can get the output. So if you are interested, you can check these papers that they map the input and kernel, and then they get the output from the convolution. But I'm not going into the detail of that because, I mean, it's not a really magic. Once you understand how that architecture works to generate the dot product, then it's a matter of how you're sweeping. So you're sweeping your essentially your filter through your input, and then you generate output based on that. So it's just a matter of changing the weights and inputs. So of course, now you can also think of using storing inputs in the weights, and then only apply the different filter as the input. Both can also be done here. You can think about it. Okay, so if you're interested, you can actually check this. This paper is actually one of them. There was a slide with I don't know, slide with the paper name. Isaac. I don't know where is it. There was a link. Yeah, but yeah, if you're interested, you can check the paper Isaac. I think we, in one of the slides I had the reference for that. It's actually one of the very first paper that come up with the use of NVM-based PIM system for convolutional neural networks. But we also use that for another work, GenPip, which essentially that neural network, the deep neural network is also used for genomics, like for base calling operation, for example. You can potentially also use this cluster architecture in order to accelerate that that neural network operations. But the problem is that these memory cells are not ideal. So we have non-ideal memory stores in the end. So this work actually is very interesting because it shows how much performance we are losing because of non-ideality that we have in memory stores. So this work actually provides a very interesting study about what would the performance impact of this architecture when we consider non-ideality of these memory stores. I think one of your colleagues was asking about the physical limitations during the break. So this one is, for example, one of the work that we try to consider what would the performance by considering physical limitations of these memories, for example. Yeah, here is the reference of Isaac from ISCA 2016. If you're interested, you can check. It's actually very much one of the first papers in the line, and also many more that you can check if you're interested. Also, in many of these cases, you are actually dealing with kind of a systolic array of computing because you have a structure that do some operations for you, like here dot product, and you need to sweep your input in order to get the whole result. So it's also, you can think of, there are also architectures with systolic array computation that, for example, this cluster, this match, yeah, exactly, these 9 boxes here in a systolic array, they can actually operate. You can use that for doing matrix multiplication. So yeah, having 2 matrices of 3 by 3. So then the output is going to be matrix of 3 by 3, right? So you're going to have 9 elements. So in all these 9 boxes, you're going to have the output of 9 elements. So now you can use this architecture to sweep, to basically map the inputs to these structure, systolic array structure, to get the output. And this idea has been used in Google also, for example. They use this tensor processing unit that they have is actually in the end is a systolic array architecture. So if you are interested, you can check this lecture. I think we usually discuss about systolic array in our digital design and computer architecture course, but we don't have time in this advanced course. Okay, so another opportunity is to merge memory and storage, as I discussed. So we have a 2-level storage model that essentially we have HDD, which is non-volatile, slow, and block address, and DRAM, which is volatile, fast, and byte address. And then these non-volatile memories combine characteristics of memory and storage. So non-volatile memories that we have, NVM, they are kind of fast, relatively fast compared to disk, of course. And they are also byte addressable, and they are also non-volatile. So you can think of non-volatile memory as a, as a kind of a cross-section of HDDs and DRAMs, right? So then potentially they can lead us designing a new memory storage model that kind of a 1 level, or unified level. So the traditional 2-level storage model is bottleneck with NVM. So the thing is that so the data which is volatile in the DRAM, the interface is with load and store operations, and persistent data is in the storage, and we need to use them with the interface of file system. So then operating at the file system with NVM actually would cause a lot of performance overhead for that NVM. So that NVM can potentially be accessed much faster with the byte addressable, but the fact that you need to operate at the file system with a file interface, a file system interface, then that would cause a lot of performance overhead for that. That's why actually people have been working a lot on improving the interface Like for example, with SSDs, I discussed about it like in the memory controller lecture. People come up with this NVMe interface, which is much faster than SATA. So that's one way of let's say, good effort through that to improve, the performance for NVM, because I mean, flash memory also can be considered non-volatile memory. But there needs to be more work in this line to come up with a better interface in general, because a lot of performance is wasted through this system software operations. So the problem, as I said, operating system and file system code to locate, translate, and also buffer data become performance and energy bottlenecks with fast NVMe stores. So the goal of this work is to unify memory and storage management in a single unit to eliminate wasted work to locate, transfer, and translate data, which improves both energy and performance and simplifies programming model as well. So now we have this persistent memory you can think of. And then in this architecture, for example, you have essentially from the system, from the processor, you have requests like load and store, and hints from software OS or runtime. This goes to the persistent memory management, which is at the software layer. And at the hardware, you have data layouts, persistent metadata and security, and different memory technologies can be actually at the hardware. So that's another way of designing, essentially, that DRAM, flash, NVM, and HDD, they are all at the same level. So then there needs to be a manager, to how to manage data, how to place data across these memories, how to move. Of course, it depends on the characteristics of data a lot. So persistent memory manager uses access and hint information to allocate, locate, and migrate and access data in the heterogeneous array of devices. So you have different devices here. Okay. So let me see. Yeah, so some more details about this PMM, which in the end, I think is very important. You check the paper for getting more information if you're interested. But it exposes the load store interface to access persistent data. So that's a huge difference here. You don't need to go through the file system for the persistent data. And applications can directly access persistent memory. So there is no conversion, translation, and location overhead for persistent data. It also manages data placement, location, and persistent, and also for security reasons to get the best of multiple forms of storage. However, it needs to manage metadata storage and retrieval. So now that we have different memory structures, different memory devices, then managing metadata is becoming more challenging. And this can lead to overheads, which needs to be taken into account when we are designing it. And it also exposes hooks and interfaces for system software, such that it enables better data placement and management for some high-level decisioning. Okay. Let me see. Okay. So a persistent memory exposes a large persistent address space, but it may use many different devices to satisfy this goal. So some of these actually devices may not be actually persistent, like DRAM, but that manager actually should make sure that everything is persistent. So there might be some locating and migrating, happening at the hardware, but in the end, when we are that interface actually allows us to consider the whole memory as persistent. So the software, the programmer does not need to deal with that essentially in the end. So that's a very good thing. Okay, so these memory devices can be, as I said, can be very different from volatile DRAM. Also, it can be to a slow and high capacity and non-volatile like HDD or flash memory, and also other NVMe devices in between. Performance and energy can benefit from good placement of data among these devices. So utilizing the strengths of each device and avoiding their weaknesses if possible. So again, we are dealing with the problem of hybrid memory. Like everything we discuss also exists here when you have different memory technologies. So you can also potentially benefit from different heterogeneity that you have across different applications. Like for example, some applications, like when we are accessing columns, in a column store that are scanned through only infrequently. So you can place them on flash. They have less locality and they are also persistent. So, but there are also some data which they are frequently updated index for example, content delivery network, that's CDN. So we can place them in DRAM. We have more locality and they are more temporally. So we don't need to place them in the flash, for example. But in the end, that manager needs to deal with that, and getting some hints from the software is very important for that. So it turns out, actually, this system is very hard to evaluate and design, but we come up with a simple system, that we could do some experiment on it. So HDD baseline, which is the baseline system that we have, traditional system with volatile DRAM memory and persistent HDD storage. Now we have this overhead of operating system and file system code and buffer. Another baseline could be NVM baseline, which we just replace HDD with NVM, but still we have this OS file system overheads because of this two-level storage model. And another way would be persistent memory, which we use only NVMs, no DRAM, but then we ensure full system persistence. So we don't need to, so we also change the interface to be one level, essentially. Yes, okay. So as you can see, by only replacing actually HDD with NVM, actually we are getting very good performance improvement. But you can also get additional performance improvement when you actually also change the interface, to be one level, and you deal with persistent memory with only load and store. The same thing also from the energy, you can get significant energy improvement when you replace HDD by NVM. This energy improvement can be actually lower if you consider, for example, HDD as a SSD, right? Because SSD is much faster. So then the importance of, so here you can actually see that the most of the improvement is coming from, the replacing HDD with NVM. But think about it in this way, that this is SSD. So then changing SSD with PCM, for example, is not going to be a lot of performance improvement. It's going to be some performance improvement, but probably lower. But then the impact of better interfacing is actually much more important. So that's why these two are very also important to consider. Okay, so this paper actually provides a lot more detail about it. So if you're interested, please check. But yeah, so I discussed about this combination of memory and storage and a unified interface to all data, essentially. And this actually is also possible. I mean, it was possible by this Intel architecture. Now, if you can get this device, this is still possible. You can come up with this library. But one key challenge in persistent memory is to how to, but any question, by the way? Okay. I'm pretty sure that I will be able to finish these slides because there are some slides that I can go over them very, very fast. But if you have questions, please stop me and I will answer. Okay. So how to ensure consistency of a system and data if all memory is persistent? So there are two extremes. We can have programmer transparent, that we can say that, okay, let the system handle it. And another extreme is that programmer only, that let the programmer handle it. And there are, of course, many alternatives in between. So we actually, again, try to be quite extreme in one of our work. We wanted to look into this crash consistency problem. And we wanted to actually handle it completely at the kind of a programmer transparent way, which is a huge overhead in the end, but we wanted to see how much we can get. So here is an example. You want to add a node to a linked list, for example. So this is going to be the previous link and then the link to the next node. So if some crash happens and if you're not careful enough and you don't handle it in a persistent way, then you might actually lose your linked list. So you might have the connection to this new link, but this new node is not connected anymore to the next nodes in the end. So then your linked list is broken. So a lot of works actually try to deal with that by using atomic structure, using also transactional memory, all this at the software layer, such that people can come up with a better programming. You can see that people need to deal with a lot of changes at the software layer in order to make sure that they they are able to overcome from these overheads. So there are manual declaration of persistent components, need a new implementation, and also third-party code can be also inconsistent, and some operations are prohibited. So there are a lot of things that you need to deal with it. So burden on the programs. So in this work, we wanted to be completely at the hardware side, to be programmer transparent. So our goal is to, as I said, software transparent, consistency in persistent memory systems. And the key idea is that we periodically checkpoint state and recover to previous checkpoint on crash. So now a new hardware-based checkpointing mechanism. So we do checkpointing at multiple granularities to reduce both checkpointing latency and metadata overhead. And also we try to overlap checkpointing and execution to reduce checkpointing latency, like using, for example, some available cores we can think of that they can also do checkpointing while we are also doing execution on other cores. And this can be adapted to NVM and DRAM characteristics, of course. In the end, we get reasonable performance, like within 5% of an idealized DRAM with zero cost consistency, but it's very hard to implement. There are a lot to do, like the overhead of checkpointing is actually very much hard to tolerate in the end. So you run and do checkpointing, you can actually also overlap it as I showed here. And then when you have a crash, you have some checkpoint that you can actually recover from that. But yeah, so this work provides a lot more detail about it. So you can check it if you're interested, but the whole overall idea, I think I provided to you. So another also key challenge in persistent memory, which is programming ease to exploit persistency. And we have looked at it in some other works. I don't go into them actually at all. So I'm just flashing them. So if you're interested, you can check these papers as well. Also, another key challenge is security and data privacy issues. Like for example, in PCM, everything is non-volatile. Potentially, if someone, for example, just detach your PCM DIMM, they can read everything. So with DRAM, we talk about cold boot attack, right? But that needs, the cooling the system to, I don't know, using some nitrogen liquid, for example, but that might not be that easy. But with PCM, for example, people can easily get the data. That's one thinking. Or for example, they can potentially use some malicious program to destroy your memory using, because of the limited endurance, right? So because of endurance problems, we have wear out attacks, hybrid memory. Now we have performance attacks, and data not erased after power off, we have privacy breaches. So to conclude quickly, regardless of challenges in underlying technology and overlying problems and requirements, these technology can enable orders of magnitude improvements and new applications and compute systems. So, but yeah, yet we have to think across the stack and design enabling systems which can overcome and provide better performance. And it's very interesting to think about flash memory, because flash memory is kind of a very doubtful emerging memory technology for at least 2 decades. But in the end, a lot of researchers and work on it, and they had a lot of issues with funding agencies as well, because they were not funding their researchers. But in the end, they made it. And now we see that the importance of having flash memory in our life. Otherwise, our smartphones, for example, would not exist. So tomorrow I will go start actually flash memory and solid state drives. But there are a lot of interesting research and design opportunities in the line of non-volatile memory. Here is some of the lists of them. Thinking about virtual memory system also for NVM is an interesting technique, direction to work on. So how to optimize the virtual memory for non-volatile memory. Like techniques like virtual block interface is one idea that can be also looked into it. If you're interested, you can check this paper and also the talk from Nasran, which was one of the PhD students in Safari. Okay, and that concludes today's lecture. Question? Was that fast? A little bit. Okay. Tomorrow we will start flash memory and solid state drives, and I'm already excited about it. So I hope to see you tomorrow.